Let's just review where things stand right now. Let me adjust this. We're talking about energy, which is a property of a system. Hang on. A property of a system. A system is just a collection of objects that are all interacting with each other. They're all applying forces to each other and feeling forces from other things. And whenever any physical process happens, energy gets moved around from one thing to another thing. And sometimes energy might flow into the system, sometimes energy might flow out of the system. And one way to get energy to move is work. Here's our rule for work. And work happens when a force acts on a moving object. So here's the displacement of the moving object, and the numerical value of work is just the magnitude of the force, times the magnitude of the displacement, cosine of an angle, and the angle is the angle between the force direction and the displacement direction. The numerical value of work tells you how much energy has been moved. Positive value of work means the thing that's feeling the force gained that much energy, and a negative value of work means the thing lost that much energy, had that much energy taken away from it. And if we're talking about a system of a bunch of different interacting objects, here's our basic rule. The energy, the total energy of that system will change in energy, if there's net work done on the system. When I write just plain W with no subscripts, that will always mean the net work done by all the external forces only. And that remember, an external force has for its source something outside the system. The internal forces don't matter. An internal force can obviously do work on something in the system, but go back to Newton's third law. For every one of these internal forces, there's an equal and opposite force, which will also be an internal force. And so inside the system, for any force, there's also inside the system an equal and opposite force, its partner force. So those two forces will always cancel out, add up to zero. So the grand total net force, when you add up all the internal forces, is zero. And of course, zero net force is going to do zero work. So the work that's done by a force that comes from one piece of the system acting on another piece of the system will move energy around within the system. It might transform one type of energy into a different type of energy. We'll see a lot of that in the next couple days. But it's not going to change the grand total energy of the system. It just shuffles around the same amount of energy, redistributes the same amount of energy within the system. This is the important thing here. Total energy of a system, of course, can consist of many, many, many different kinds of energy. For our purposes, we look at only 4 types of energy. So a change in the total energy will be due to just possible changes in one or more of those 4 different types of energy. And what are those types? First, there's the type we've already thought about a little bit, kinetic energy. And then there's something called gravitational potential energy. Whenever we're talking about a potential energy, we'll use the symbol U. And then change in elastic potential energy, and then change in something called thermal energy. Let's explain these things one at a time. So we already know about this. Kinetic energy is energy that you have by virtue of motion. If you're moving, the velocity is not zero, so the kinetic energy is not zero. What about this next one? Gravitational potential energy. Let's look at that. Let's keep this on the board. Imagine I'm holding this piece of chalk and I'm moving it up at a constant velocity. So at some point after I've started, I start watching it and then continue watching it until it moves up to here, but it doesn't stop here, it just keeps on going. In other words, when it gets to some initial elevation or height, I started moving it lower than that. So it's got some velocity, not zero, when it gets to that height, and then it rises up to some final elevation or final height, but it's maintaining a constant velocity. So the final velocity up here is the same as the initial velocity. I don't stop moving it until it gets farther above here. So I'm watching the chalk go through a displacement from here to here. So there's my displacement vector, which always takes you from the starting point to the finishing point. And the force from the normal force from my hand pushing up on the chalk did work, because there was a force acting on this chalk while it was moving. So how much work? Let's figure that out. So work is, of course, the magnitude of the force, just the magnitude of the normal force from my hand on the chalk, times the magnitude of the displacement. Displacement is this distance, so we can think of the magnitude of the displacement, in other words, the total distance between here and here, as just the difference between these elevations. That'll turn out to be a good way to write that. So final minus initial elevation. And then the third term is cosine of the angle between displacement and force. The force from my hand on the chalk is a normal force, which always points perpendicular to the surface. The surface in this case is my hand pushing up. Normal force is up, displacement is up. Both the displacement and the force are in the same direction, so the angle between displacement and force is no angle at all, or 0 degrees. So the last term is cosine of 0 degrees, which is just plain +1. So the work done, in this case, is positive. I've given energy to the chalk. I've given this much energy to the chalk, whatever the numerical value of this turns out to be. But same speed at the start and the finish. So the change in kinetic energy, which is just the final value of kinetic energy minus the initial value of kinetic energy, is 0, because this number is the same as this number. Final speed is the same as initial speed, so the final kinetic energy is the same as the initial kinetic energy. So even though I gave energy to the chalk, that increase in the chalk's energy does not show up as an increase in kinetic energy. Therefore, there must be some other kind of energy that increased. And that other kind of energy that increased, in this particular case, we call gravitational potential energy. And from all this, we can actually get an equation that will allow us to calculate gravitational potential energy. First, we go back and remember that I'm moving this chalk up at a constant velocity. Constant velocity is just the same as saying zero acceleration, because acceleration measures the rate at which velocity changes. Newton's second law tells us that if there's no acceleration, that's because there's no net force. No net force tells us that the two forces on this chalk have to cancel each other out. They have to have the same magnitude. There's only one upward force, the normal force from my hand, and there's only one downward force, the weight. So if those two forces are canceling out to give me zero net force, the strength, the magnitude of the normal force from my hand must be just the same as the magnitude of the weight, m times g. Okay. So, in this case, the work done, which is changing the energy of that chalk, is what? It's just the magnitude of the force, which is the same as, turns out to be the same as the weight in this case, times the change in elevation. Let's do the distributive rule on this, and we say mg final elevation minus mg initial elevation, higher elevation at the end, lower elevation at the beginning, so this difference here is positive, just as it has to be because positive work was done. There was a positive change, an increase in the system's total energy. But that increase in the system's total energy did not show up as an increase in kinetic energy. Instead, it shows up as an increase in a different kind of energy. It shows up as an increase, a positive change in gravitational potential energy. And like any change in anything, that's just the final value minus the initial value. So if you compare this to this, see that this, which just corresponds to the final value of gravitational potential energy, and this corresponds to the initial value of gravitational potential energy. So we can then say, got a rule for gravitational potential energy, m times g times elevation. One important point, right? Elevation depends on how you set up the coordinate system. It depends on where you put the zero level of coordinate for the coordinate system. And as we'll see, as you'll see later on, you're free to put the zero level of elevation anywhere that's convenient, and it won't change any of the important results. Like I said, we'll see how that works in the upcoming days. So now we have two kinds of energy that a system could contain: kinetic energy from any moving things inside the system, and then gravitational potential energy. And so any change in the total energy of the system, which happens when work is done by external forces, could show up as a change in kinetic energy or a change in gravitational potential energy, either one. Now, for a third type of energy, that was elastic potential energy. So specifically what happens there is if you take an elastic object, and our standard model for all elastic objects will be just a spring, imagine stretching or compressing that spring, distorting the elastic object in some way. Whenever an elastic object is distorted, you've done work on that object and you've given it energy. Specifically, you've given it elastic potential energy. Let's see how that works. So imagine a spring, one end is fixed, not moving, attached to the wall here, and the other end you can either pull on or push. But when you're neither pulling nor pushing, let's say that the spring in its natural state, undistorted, unstretched, unsqueezed, is just this long. So there's where the right end of the spring sits. And if you pull on the spring or squeeze the spring, the right end of the spring will experience a displacement. It'll experience a displacement while you're applying a force to the spring to either pull it or squeeze or push on it. So work is done because the spring is moving while it feels a force. Well, let's say you pull on the spring. So here's the initial location, and then you pull it this far. So now the right-hand end of the spring is up here. Here's the final location. So that the right end of the spring has experienced a displacement that took it from here to here. And of course, while you were pulling on the spring, your pull is also a force to the right. Now, back to Newton's third law for just a minute. Newton's third law tells us that if you're applying a pull, that if you're applying a pull to the right from you on the spring, then that force has a third law partner. That third law partner is a pull, it has to be the same type of force, a pull in the opposite direction, a pull to the left, from the spring on you. Remember, it's always the case in a third law pair that if one thing is the source of a force, in this case my hand is the source of this force, then that'll be the thing that feels the third law partner force. Right? My hand is pulled on by the third law partner force, which comes from the spring. So there's then a force on hand from the spring. And that kind of force we usually refer to as a spring force, and there's a rule that tells us all we need to know about that spring force. That force on my hand from the spring minus K delta x, where delta x is just displacement, final position minus initial position. Which is what I was calling D here. Same thing. D is just another name for this, same thing. Now this K here, I'm going to write it as a lowercase k to distinguish it from kinetic energy. This is not kinetic energy. Don't make the mistake of confusing this for kinetic energy. This is not kinetic energy. So what does this rule tell us? It tells us that the force is in the opposite direction from the displacement. That is, if the spring is stretched to the right, that is, this displacement points to the right, then the force on you when the spring pulls back is in the opposite direction. And the other thing it tells us is that the magnitude, the strength of this force is proportional to the amount of distortion, proportional to the length by which you stretched or compressed the spring. This works if just as well if the displacement is caused by a compression, pushing the spring to the left. The proportionality constant K actually means something. Let's think about what it means. So the magnitude, let's just think about that equation in magnitudes. The magnitude of the spring force, the force of the spring on my hand, divide both sides of that equation by K. So the magnitude of this side has to equal the magnitude of this side. Magnitude means magnitudes are positive, so the magnitude of this factor of -1 is just 1, and then the magnitude of this, like that. Okay, just do some algebra, and that's what K is. Let me go back here, come on. Oh, come on. All right, there. So K is just a certain amount of force divided by a certain amount of distance, newtons per meter. What K means is how many newtons of force are needed to either stretch or compress the elastic object by 1 meter. And then a small value of K means it's a very easily stretched or compressed object. A small value of K means a small number of newtons will stretch or compress the thing by 1 meter. A big value of K means it's a much stiffer object, harder to stretch or squeeze. So say K equal to 1,000 newtons per meter means it will take 1,000 newtons of force to stretch the spring by 1 meter. That, say in the case of a spring, big K means it's a very stiff spring, and a small K means it's a very soft, squishy spring. Say the suspension system in a car, you can think of as a bunch of springs, which would all have very, very, very large values of K. Okay, now back to potential energy. Let's go back to that spring. Start here, pull it until it's the right end of the spring is here, so the spring is now this much longer. There's the final location of the right end of the spring. So the spring was displaced by that much, and the displacement is just, that D is just another name for delta X, which has been our more common way of saying displacement. But there was this force acting on the spring while it experienced this displacement, so work was done. How much work was done is a little trickier in this case, because as you just saw when talking about the spring force, that force is not constant. The spring force pulling on me is just the third law partner of this force. So this force is not constant either. The spring force gets stronger the farther I pull the spring. So this force gets stronger the farther I pull the spring. So this force is not constant. Our actual equation for calculating work, strictly speaking, is good only for a constant force. The book describes how you have to think about it differently if you have a non-constant force, but for our purposes, what's important is only the final result, and that is the elastic potential energy is just 1/2 K, the same K that appeared in the equation for the spring force, once again, not kinetic energy, times the displacement squared, or magnitude of the displacement squared. And specifically, this always refers to displacement away from equilibrium. So in other words, before I started pulling on the spring, there was no net force on the spring was in equilibrium. So xi really amounts to the equilibrium position of the right end of the spring, and then in the final state I've pulled it this far. So in the final state, so in the initial state, the displacement away from equilibrium is 0. In the final state, the displacement away from equilibrium is that. Okay. Now, when I did work, I knew it was positive work because the displacement and the force on the spring were pointing in the same direction. So that cosine factor was cosine of 0, in other words, positive 1. And then the other factors in the work equation are magnitudes, magnitude of force, magnitude of displacement. And magnitudes, just by definition of magnitude, are always positive. So all three factors in the work equation were positive. So the work done on the spring was positive, which means the energy change in the spring was positive. So the spring's energy changed, but again, kinetic energy did not change, because when I first started pulling on the spring was not moving. So velocity of 0, and therefore kinetic energy of 0. And when I've finished pulling on the spring's velocity, again, is 0. So the kinetic energy, again, is 0. So the change in kinetic energy, 1/2 mass final velocity squared minus 1/2 mass initial velocity squared, but the final velocity and the initial velocity are both 0. So 0 there, so the final kinetic energy is 0, 0 in that factor, so the initial kinetic energy is 0. So the change in kinetic energy, comparing just the start to the finish, the change in kinetic energy is no change at all. The kinetic energy is the same at the beginning of the process as it is at the end of the process. So the increase in energy does not show up as an increase in potential energy. Does not show up as an increase in kinetic energy. And then furthermore, the increase in energy does not show up as an increase in gravitational potential energy either, because this all takes place on a horizontal plane, so the elevation is always the same, which means gravitational potential energy is always the same. gravitational potential energy does not change. So that's a positive number. There's an increase in the system's energy, but that's zero and that's zero. So there has to be a third type of energy, and that type of energy is what actually increased. And it's the elastic potential energy in this case. Remember, elastic potential energy is energy that's given to an elastic object when you do work on that object such that the object is distorted. Right? In the case of a spring, it's either stretched or squeezed. And then there's one more that we don't have an equation for, but it's important to think about. Thermal energy. Thermal energy is just the total energy, total kinetic plus potential energy of all the atoms and molecules in the objects that make up the system. For our purposes, the most important way you can get a change in thermal energy is by friction. And we see an example of that. Let's say if we're rubbing our hands together, we feel our hands get a little bit warm. That's because the actual temperature at the surface of our hands rises a tiny little bit. And temperature, we'll see this in the last couple units, temperature is actually how we keep track of the kinetic energy of molecules. So higher temperature specifically means that the average molecule has a higher speed, or the average speed of molecules has increased. Well, if average speed increases, that means average kinetic energy has increased. So the energy has increased because work due to friction moved some energy around. In the second half here, I'll look at a couple examples of how we can think about all this stuff.